is coming to us online. Reza Mahmoudi. Reza is a former postdoctoral fellow at TAU and senior transportation planner at GFT USA. He likes hiking, baking, and cooking Persian and Turkish cuisine. His research interests include public transit, on-demand transit, microtransit, and shared mobility with CAVs. And his presentation will be about T-Spark, Transit Service Performance Analysis and Redesign Kit. Reza?
Thank you, Brandon, for the introduction. Can you see my screen?
Yes, we can.
Okay. Just a minute. And yeah, hello, everyone. My presentation will be on T-Spark Transit Service Performance Analysis and Redesign Kit. And for the sake of time, today I will just focus on generally introducing T-Spark and showing what kind of tools it includes and how we can use T-Spark for analysis. The main motivation behind T-Spark was to develop a platform which enables transit agencies to conduct a comprehensive performance evaluation of their existing transit service and figure out strategies and solutions to improve the quality of provided transit service. So the objective was to develop a tool that localizes the performance evaluation process, conducts a relative multi-period performance evaluation at both route and segment levels, identifies source of inefficiencies, proposes the best solutions to improve the performance of inefficient transit routes and segments. The main advantage and the main difference between T-Spark and other similar tools is in the methodology embedded in the heart of T-Spark, which call it data envelopment analysis, or DEA. Yeah. Traditionally, when it comes to evaluate the performance of a transit service, a transit route, transit agencies have a list of KPIs, their own standards. They quantify those KPIs and they make decision based on the value of those KPIs for that specific transit route. But we suggest using DEA. Yeah? DEA models deal with related performance evaluation. They first categorize KPIs into two different categories: inputs, outputs. Inputs are those KPIs which are kind of costs in our service, and outputs are kind of benefits of our system. Then they assume that each transit route acts as a system which takes inputs and produce outputs. And instead of focusing on a single transit route, they do the performance evaluation of a transit route in the presence of all other transit routes in the network. That's why we call it relative performance evaluation. So let's start by generally introducing T-Spark and tools that it includes. So as I mentioned, the current version of T-Spark is a web app. The main purpose is to enable transit agencies to conduct a performance evaluation process, identify source of inefficiencies, and find the best strategies to redesign or replan transit services to achieve higher level of efficiency. T-Spark includes 6 different tools. We have demographic analysis, coverage analysis, and access analysis tools, which we always need for any transit planning studies. We have tool for adjacent network analysis, which I will talk about it later. And 2 main tools in T-Spark are DA engine and performance evaluation. In order to use T-Spark, you don't need any unusual data set. Basically, whatever you, as a transit agency, you are using always for your performance evaluation, you can just feed them to T-Spark and do your analysis. your shape files, GTFS data, parameters for your analysis, demographic data that you have, and of course, KPI values that you have in your analysis for your transit service. Let's start with access tool. So in the current version, TSpark has the feature of analyzing the access to 4 different type of services: grocery, hospital, jobs, and schools. You choose one of these services. You just upload the GTFS data and other required shape files and data. You choose the day of the week that you want to do your analysis for that, the operation period that you want to do your analysis based on that, like AM peak, PM peak, off peak, overnight, etc. You set the parameters for the users, and then you choose the base map format for your analysis and just run TSpark. And you will see the results of the access for the zones that you have selected. TSpark enables you to do your analysis in different level of zones, like a TAZ level and any other zonal level that you have data for that. So if you click on each zone, you will see details of the access analysis for each zone separately. Here, for example, you see the results for access to grocery within the city of Mississauga for a regular weekday during AM peak using public transit. Demographic analysis. If you have any data related to the demographic, you can use this part to visualize them. Again, select the level of zone that you want to do your analysis, upload required data, shape files. If you want to do this analysis for the whole city, or you want to do this for a part of the city, and then just run TSpark and you will visualize the demographics for your city. Coverage analysis. In the current version, we have 3 alternatives to do our coverage analysis. First, you can do this analysis for the whole transit network. Second, you can do this coverage analysis for a set of selected transit routes to investigate their catchment area. Or you can do this analysis for the opposite side. You can analyze the transit deserts within the city, those areas that are not being served with any transit service. Again, just upload the required data. If you want to do analysis for just a set of transit routes, select the targeted routes and then run TSpark. For example, here you see the results for transit deserts for city of Mississauga based on a regular weekday and AM peak operation period. Sometimes we need to analyze the overlap between a set of transit routes and another set of transit routes, and between the catchment area of a transit route and another the catchment area of another transit routes. Adjacent network analysis tool provides us this opportunity to do this analysis. You just select the set of transit routes that you want to analyze their overlap with another set of transit routes and just run TSpark. But let's move to the 2 main tools that we have inside TSpark. First, DA engine. So we assume that each transit agency can have actually 3 major objectives by doing their performance evaluation. First of all, they can say we are happy with the benefits, with the outputs of our transit service, but we are unhappy with the cost, with the level of cost that we are inputting to the system. So we want to have the same level of output, but with less costs. How we should do that? Or they can say, okay, we are happy with the level of costs, but we want to achieve the higher level of benefits. Or they are unhappy with both of them. They want to achieve high level of benefits with less level of costs. On the other hand, from methodological perspective, from the approach perspective, they can do this performance evaluation for just a single period or for multiple periods, or they can use just traditional approach, what we call in TSpark as absolute efficiency scores. So combination of these objectives and the possible methodologies that the transit agency can use, we have embedded 19 sophisticated optimization models in the DA engine that transit agency will use to produce raw data which reflects different aspects of the performance of transit network within an operation period and evaluation period. Then we can fit this data for the next tool, which we call it performance evaluation tool. So basically, this tool is a tool to translate those raw data obtained by a data engine to a plain language, understandable by a transit planner, by managers, etc. So we will upload those data, we will fit those data created by the engine to performance evaluation tool, and we will visualize data. We will analyze the previous data. For example, just as an example, we can visualize the whole transit network based on the average efficiency scores that we have obtained for each transit route for a specific operation period. We can use this tool to analyze the fluctuations in the performance of a transit route during an operation period. Or we can use this tool to see the actual, or what I call it, fake positive or negative changes in the performance of a transit route in a specific time period, and the reason for those fluctuations, for those fake or real fluctuations in the performance of transit routes. Okay, let's see some example results of T-Spark for a real project that we did for the city of Mississauga. So similar to any performance evaluation process, the first step to use T-Spark in our analysis is to identify the list of KPIs. For the purpose of our case study, we started by reviewing the literature and also reviewing MyWay's service standards. MyWay is the transit agency of City of Mississauga. So we prepared a long list of all possible KPIs that we can use for our evaluation. We provided this list to the city and we asked them to give us the final list of KPIs based on their standards and their objectives. Second, I mentioned that T-Spark is capable of doing analysis in both route level and segment level. So in the next step, we need to divide transit routes to multiple segments. The easiest approach is to assume that distance between two consecutive stops is a segment on a transit route. But in a real world, we know that this distance is so very short, making it meaningless to conduct a performance evaluation process for this short distance. So having the results of this, having the list of KPIs and the list of segments, then we can run a T-Spark and identify source of inefficiencies within the network, and of course find the solutions-based strategies to deal with these inefficiencies. For the case of the city of Mississauga, we decided to have 5 inputs, KPIs that reflect the cost in the network: vehicle capacity, frequency, operating kilometers of routes, number of stops, and number of transfer stops. And we decided to have 5 outputs: load factor, boarding per service hour, cost recovery, actual on-time performance, and user satisfaction. In order to divide the transit routes to multiple segments, MyWay suggested us to use time points to divide routes to multiple segments. So basically, time points are those stops that we have enough space. In most cases, we have enough space to park a bus, making major traffic in the surrounding area. So we use major time points to divide each transit route to 3 major segments in our network. And I should mention that in this analysis, we used provided data by MyWay for almost 21 months. starting by January 2023 to September 2024. And I want to mention it here that for the purpose of this analysis, just for the case of Mississauga, whenever we face an inefficient transit route or segment, we have three alternatives. We can redesign or replan operation of transit service for that inefficient transit segment or route. Second, we can just remove it. Third, we can remove it and replace it with the on-demand transit service. So if we use T-Spark to do our analysis in route level and map the transit network based on the efficiency scores obtained for each transit route in each operation period, I mean each month, we will see something like this. As you can see, we are experiencing a huge amount of fluctuations in the performance of transit routes during these almost 2 years, emphasizing the importance of conducting multi-period performance evaluation instead of doing our analysis just for a specific time period and make long-term decisions just based on that specific operation period. And if I take this analysis to segment level and do the same for segments, we will see even more details and more fluctuations in our network. Okay, let's focus on the segment level analysis. If I map the transit network based on the average efficiency score for each segment during these almost 2 years, we will see something similar to this. Just looking at this map provided by T-Spark, we can see a lot of details about the performance of our transit network. For example, if we look at the southern area of the city, we will notice that almost all segments, transit segments that we have in this area, they have very weak performance. They are super inefficient. So we need to come up with some strategies to improve our service in this area. Just for the purpose of this presentation, let's focus on Route 8 and segment 8A, the green one, 8B, the yellow one, and 8C, the black one, and see how T-Spark helps us to find the best strategy to deal with these inefficient segments and how we can improve their performance. If we look at the results of T-Spark for segment 8A and 8B, we will see that the average efficiency score for 8A was almost 80%, and for 8B was almost 60%. But the maximum efficiency score that they have touched was almost 90%, which shows a good potential for these segments to be efficient, to perform much better than what they are doing right now as a fixed route transit segment. So our results suggest to keep these segments as a fixed route transit segment and improve their performance just by redesigning them or replanning their operation. But we have a lot of more evidences that support this idea. For example, if we look at the other results of this Spark, the results provided by Malmquist Productivity Index, which shows actual change in the performance of these transit routes, we will see that actually during last 2 years, the overall performance of these segments, the efficiency change in these segments, and technological change in these segments had a positive improving trend. So based on these results and all of the other results of T-Spark, we suggest to keep these segments as fixed route transit segments, but improve them by replanning them. How to replan them? T-Spark as answer for those as well. So for example, we have surplus and slack values for our KPIs obtained by T-Spark. It says, for example, for 8A, if you want to improve its performance, you need to, just an example, you need to shorten the length of this segment by 1.15 kilometer. It means that the length of this segment is much more than what we really need based on the demand and the structure of the area that we have. Or we need to remove 5 stops from this segment. So we do not have in that higher amount of demand that satisfies having this much number of stops. Or from vehicle capacity perspective, it says that we need to dispatch smaller vehicles for this transit route. We need to reduce the capacity of vehicle by 20 seats. And also another important thing is reference sets that T-Spark provides for each segment. Reference sets are those super efficient segments which have highest similarity with segment 8A. So for example, for 8A, we have 11A. It means 11A is a super efficient segment and it has highest similarity with 8A. So if you look at 11A to see what you are doing there or what you're not doing there, it will inspire you how to improve the performance of 8A as well. But let's focus on 8C. Looking at the results of this one for 8C, we will see that the performance, the average efficiency score for 8C is 10% for 2 years. And the maximum that it has touched is almost 40%. So for now, we are pretty sure that keeping them as fixed transfer is not a good idea. But should we remove it or should we replace it with on-demand transit service? Again, if we use other outputs of T-Spark, like access analysis, demographic analysis, for example, we see that if we remove this 8C, we will have a huge transit desert within an important area of the city, which is not desirable for the transit agency. So removing is not an alternative for us for this specific segment. So we say remove it and replace it with on-demand transit service. If we do this analysis for all other segments using different tools of T-Spark, combining the results of different tools, we will find the optimal solution, optimal strategy to how to improve the performance of these inefficient segments in all areas of the city. As summary, T-Spark has some key features: unified transit data engine, interactive geospatial maps, DA-based efficiency, and Monquiz productivity index analysis. It's capable of conducting scenario-based analysis, and it has some advantages. T-Spark can be used to do relative network level multi-period performance evaluations. It's capable of identifying source of inefficiencies, detection of true productivity increase and decrease, evidence-based decisions by combining quantitative analysis, spatial analysis, and productivity analysis in one place, faster analysis cycles by repeatable pipelines, finding under or overserved areas in order to design more equitable transit services, conducts, and of course, T-Spark is capable of conducting both route level and segment level analysis. Thank you so much for your attention.
Thank you, Reza. Any questions in the audience here? Online?
Nope.
Reza, I guess one thing that's very interesting is the analysis by segmentation that the DEA allows. But I was quite curious about the evolution of the performance and how much it the variations over time. How do you explain that? I mean, I doubt the actual characteristics of those lines changed that much over that time. I was just curious.
Yeah, We had two actually major reasons for the fluctuations that we had in the performance of our transit routes or segments. We call it technical changes or technological changes. So technical change comes because of the fluctuations actually in our inputs and outputs. So demand increases, demand decreases during the operation periods. There's a specific event in the city in a specific evaluation period. So we are experiencing increased demand for the whole transit service. We have technological changes when actually transit agency plays with the design of branches, with the number of stops, with the service frequency. So that's those we call them technological change. So these two changes are the main sources for fluctuations in the performance of our transit routes and segments.
Okay, thank you very much. Any questions? Okay, well, thank you. Oh, wait a second.
We have one online question. So the question says the route and segment analyses were interesting. What is the advantage of the monthly segmentation of the time dimension when compared to aggregating a year?
So based on the DA concept, average efficiency score doesn't mean anything because of this fluctuation, because of these technical and technological changes. So the only reason that I used average score was to show the average performance of the average performance of the transit network, to give you some ideas. For the real analysis that we did, we analyzed the results for each operation period separately. So we didn't use the average efficiency score or aggregated results for a specific year. That's one thing. Another is that if we just use the aggregated data, KPIs for a specific year, still we are missing a lot of details here. The seasonal effects, the policy changes, specifically technological changes that are happening from one season to another season, from a week to another week, from weekday to weekend. So again, that was another motivation to do our analysis for each operation period separately. They answer your.
Yeah, thank you.
Okay, well, thank you very much.
Thank you.
Jillian? So we're switching back to we're going to be going back and forth a couple times, but I'll let Jillian set up. But Jillian Song is a PhD candidate. His research focuses on scheduling. Jillian Song is a PhD candidate here. His research focuses on scheduling and planning decisions for public transit operators. He enjoys exploring transit systems, especially riding trains and in new cities when traveling. And his topic is real-time assignment of spare board transit operators.
Okay. Thank you, Brandon. Hi, my name is Jillian, and welcome to my presentation on real-time assignment of extra-board transit operators. This work deals with the workforce planning and scheduling aspect in public transit, and this paper was done in collaboration with my supervisors, Professor Amar Shalabi and Professor Merv Fedor. So this presentation will be divided into 5 parts: the introduction, problem definition, methodology, results, and conclusion. So I will start by introducing the important terms that you will see throughout this presentation. So normally, public transit is about providing service to the users according to a predetermined schedule. But in daily operations, oftentimes operation tasks comes unassigned for a variety of reasons, and they become what's known as open work. So the most common reason for open work is the unscheduled absence of regular duty operators. And this is a big issue these days because it is known that urban bus operators have much higher absence rates than the average blue-collar work. And for this problem, open work is stochastic in nature because you don't know when it's going to arise. Therefore, it introduces uncertainty to the scheduling process. So to deal with open work, transit agencies have a roster of so-called extra board operators. These are also called spare board operators in Canada. And unlike regular duty operators, these operators do not have fixed sets of trips to operate on a daily basis. But they are mostly still full-time employees at their transit agencies. So they're subject to the same union rules as other full-time employees. And it is a common practice to place newly trained operators on the extra board roster. And I'll go through the main decision levels in the extra board scheduling framework. So the highest level, strategic level, is about the overall hiring decisions. And at the tactical level, so these are decided every sign-up period. So that's like every 3 to 4 months. So these decisions are about sizing the number of extra board by garage and by day of the week. And at a lower level, we have operational decisions. So these are about deciding the report times for the available extra board workforce. So the report time is essentially a time where you ask each extra board to show up at the garage and wait for further assignment decisions. And then lastly, we have the real-time decision level. So that's the focus of this study. So open work can arise at any time during the day. And our decision is to assign extra boards at a real-time basis. So we take a quick look at the two higher decision levels, the tactical and operational level decisions. So these are also challenging problems because the transit supervisors have to consider the uncertainty in open work that's going to arise after decisions are made. So in practice, a lot of the times, supervisors just use sort of rule of thumb methods to make these decisions regarding sizing and report time determination. And in the literature, these may be formulated as stochastic optimization models. So I actually have done a paper that specifically looks at the operational level decisions. And I formulated the problem as a two-stage stochastic program. So looking at real-time decisions, so these are even less frequently addressed in the literature. To the best of our knowledge, there has only been one study that's specifically looked at this. And they conducted a case study on transit agency, and they noticed that even at the same garage, at the same agencies, different supervisors may have like varying methods in terms of assigning extra boards on the real-time basis. So that goes to show how there's really no unified method in doing this. And the authors there proposed a randomized online algorithm for these decisions. And in this study, we propose to model the real-time model as a Markov decision process, or MDP in short. So this is designed to capture the sequential nature of the problem. So moving on to problem definition. We introduced two important sides in the problem. So we have the demand for drivers in the form of open work, and the supply of drivers in the form of the extra board roster. So the main decisions are really to match the two sides together. And in this study, we specify that each garage at the agency can collaborate among its own and basically act as one single decision maker. And the planning horizon is going to be 1 day of operation at the garage. So for example, that can be early in the morning to early in the morning of the next day. And the workday will be discretized into sub-periods of equal length. So for example, we've chosen 15-minute sub-periods. And now let's take a deeper look at open work. So open work can, the most common way open work occurs is the absence of a regular driver. And here we define a concept known as a work piece. So a work piece is the smallest unit of task that must be performed by a single operator, and it cannot be broken up. So for example, we have this driver who's assigned to operate between point A and B in 3 round trips. So we can say that each round trip is a work piece where they have to be there for the whole round trip. And if this regular driver is absent, all 3 of these work pieces are open work pieces. And now we look at the daily workflow of an extra board driver. So each driver will have an assigned report time. So for example, that's 6 a.m. And if their shift is 8 hours long, then you know that they will end their shift at 2 p.m. So at the beginning of the day, they show up at the garage, and there may be some administrative tasks to handle that takes 15 minutes. And then they're assigned to 2 round trips of Route 5. These are 2 open work pieces. And then they come back at the garage at 11. And after that, they're ordered to hold at the garage for another 30 minutes. And then they finish their day by covering another round trip on Route 7. So yeah, so that's an example day of an extra board. So how do we encode all of this into the MDP representation? So suppose that we have a state at a decision epoch T, let's say that's 7 a.m. So in the state, we want to capture the states of both the demand side and the supply side. So the demand side is the current open work pieces that needs attention. So for example, we have these 2 work pieces. And for the supply side of extra board drivers, we capture their state by this tau variable. So this shows the next period when each extra board will become available. So whether that's the next period when each driver comes back from their current work, or for drivers that hasn't reported yet, that is their report time when they do show up. So you see that at 7 a.m., we have these 2 available extra boards. And the decision is to match these current drivers to the open work pieces. And also another possible decision is to hold these drivers for 1 period and not assign them to any work piece just yet. And from these decisions, we evolved into a post-decision state, T, by updating the states of both demand and supply. And as more newly opened work pieces are revealed, we transition to the next stage. And this continues towards the very end of the planning horizon. So now we go to the solution methodology. So our goal is really to find a policy that maps a certain state to the optimal decisions of that state. So the tricky thing about this problem is that each extraport driver may have different report time or shift lengths. So that makes them very heterogeneous among one another. So that means we have to look at this problem from the perspective of a single extraport driver. So with the index j in this case. So for this driver, we know their report time and their end time. And suppose we're at a decision epoch t that's in the middle of their shift. So they've done some work in the past and they're available right now. So let's say we assign them to this round trip. So by doing that, we capture some immediate reward from this action. So this reward can be understood as the cost savings from preventing this round trip from being lost. So this is kind of a social benefit. And then after that, they're expected to finish their work at the end. Let's call that T0. So from T0 to their shift end, in this remaining duration, they have future value in the form of assigning themselves to open work pieces that haven't been revealed yet. And we denote this by this V bar value for expected future value. So this future value thing is pre-trained using a backward dynamic programming method. So in the interest of time, I'm not gonna go into the details for that. And of course, another possible decision is just to hold this driver. So that has no immediate reward, but they become available at an earlier time. So that means their future reward is gonna be higher from this action. Yeah, so the proposed policy at a given state in the given decision epoch, the optimal decisions are obtained by solving an integer linear program. We make decision variables that indicate whether each available extraport is going to be assigned to every eligible workpiece. And we add constraints to specify what can and cannot happen with these assignments. And the objective is to maximize the sum of both the intermediate plus the future rewards for all the available extraports involved in the decision. And now let's move on to the results. So for this numerical experiment, we looked at 7 bus routes that's operated by the mountain garage of MyWay. So MyWay is the transit agency for the city of Mississauga. And we obtained their weekday schedule from the city's open GTFS feeds. So this is a daily profile of the number of active drivers throughout the day at each 15-minute period. So you can clearly see the peaks, AM and PM peaks. And the workday spans from 4 a.m. to 3:30 a.m. on the next day. And in total, there are 87 regular duty drivers scheduled with a total of over 600 driver hours. So now we try to simulate the open work that's going to arise. So we have 2 sources. One is the absence of regular drivers. So we define a predetermined absence rate for these drivers. And there's also these extra trips being dispatched. So these occur more frequently during peak hours as a response to demand surge. And we simulated 1,000 scenarios of openness outcomes of the work pieces. And overall, the amount of open work is about 12% of all scheduled work. And we also generated these higher level decisions. So in terms of extraport sizing, we use a simplified method to get a baseline reference of about 10 extraports, but we're going to conduct sensitivity analysis with various extra board sizes. And then the report times, we simply used a heuristic method that was previously proposed in the literature. And we test the performance for 3 assignment methods. So first, we have the proposed policy of the study. And second, we devised a myopic assignment policy. So that tries to emulate what sort of happens in the real world. And third, we have the perfect information. So perfect information is like saying every single open work piece is revealed at the very beginning of the workday. So the transit garage has full information of where you should assign each driver. So obviously that's not realistic, but that sort of acts as a theoretical upper bound performance. And performances are going to be reported by an average of all the 1,000 simulated scenarios. So now we look at the reward with some different test scenarios. So here we chose a pretty simple reward weight where we just look at the total amount of open work hours that are covered by extra boards. So as expected, increasing the number of extra boards in the x-axis does help cover more and more open work hours. But even at 14 extra board drivers, there's still some gap with the actual amount of total open work. And we also see that the proposed policy does outperform the myopic policy. And we also took a look at the utilization rate of the extra board roster. So the utilization rate is defined as the total amount of open work, the total amount of productive work that extra board drivers are using, divided by the total amount of shift they're assigned to. So for example, out of the 8-hour shift, if they just have 4 hours of productive work, then that's a utilization rate of 50%. So we see that as you increase the number of extra boards, the expected utilization rate kind of goes down across the board. And yeah, that concludes my presentation. So in summary, we studied the real-time assignment problem for the extra board drivers. And the problem is formulated as a Markov decision process. And as an extension, we're trying to look at how to incorporate overtime drivers into the decision making, because like oftentimes transit agencies don't rely solely on extra board drivers to cover open work. They can also have regular drivers working overtime for this purpose. But of course, there's a trade-off in the cost and as well as driver satisfactions, and that's in the works right now. Yeah, and yeah, thank you for listening. Thanks.
You weren't talking about the welders. I met one a couple of weeks ago, early morning on a train, and he told me they had sent him to phone in sick during his regular hours so he can make 2 times time when he comes in emergency times. But I'm wondering, did you find any patterns in your data that might help normalize based on weather or other conditions? To be able to predict, how many people were not going to show up.
So you're talking about sort of a prediction of the...
Yeah, like trying to anticipate, if at 5 a.m. there's 5 drivers not there, then maybe at 2 p.m. or the next major group of them will be an equivalent proportion or something.
For this work specifically, no, because for these operational level decisions, we assume that we know how many extra board drivers there are going to be. like even if you know there are going to be a lot of absences, like the extra board one, but yeah, this is a very important question. Like that deals with the sizing of the extra workforce and there's definitely things you can do.
In your perfect world, if you didn't know what's going on, obviously that is perfect. How do you predict that? Yeah.
How do you predict like when people become absent, for example? Yeah, I guess you would have to look at historical data. Yeah, so for this work, I didn't really look into that, unfortunately. But like this kind of data is kind of sensitive because it involves personal information. But yeah, that will definitely be super valuable if we do get this kind of data and look more into it.
I guess maybe you could go through a little bit more how you see it being used. Is it at the beginning of the day, given what they know, which is an imperfect knowledge, or is it at every point during the day, every time there's a new absence? When would the data be? When would the analysis be used?
So for this model specifically, it'll be used at every like what we call sub periods. So every 15 minutes, you look at the state of the system, like how much open work there is and how many drivers you have right now, and you make decisions every 15 minutes.
Okay.
On the go, yeah.
Okay, so the system itself would generate that based on all the inputs.
Yeah, exactly.
Like there you go.
So my question is also kind of on the forecasting side. So I think this research that you presented was like about real time, like estimating how many, spare boards you need and where they should be deployed. But is there a way to kind of build upon this research so that you can then forecast how many people you're going to need at any given time in the future? For example, or like you're saying we have to make this decision like every 15 minutes. Is there a way to kind of make a decision at the beginning of the day that could possibly be applied throughout the day and not have to do it at every 15-minute intervals? Just curious if you have any thoughts on that.
And so for this model I assumed like kind of a static absence distribution, but if you do have historical data available, so for example, on Mondays, you know that there are going to be more absence, like at, for example, 8 a.m. You can try to like reallocate your resources like so that you have more extra boards available at 8 a.m. Right? But for this, but going back to the problem with making assignments every 15 minutes, that is the flexibility of this model, because being able to do this means you can respond to things very quickly, right? Whenever there's something like an emergency or whatever, you have the frequency to, like your decision is frequent enough so that you can respond quickly. Yeah.
Jillian, I know you talked very quickly about phase one of your work, the operational level. So how do you envision combining both? If you can just explain to the audience your vision of really having, because you're dealing with the same problem, but at different levels or different decision-making points. So if you can just talk about this, thank you.
Yeah, so the question is about how to combine the report time determination and this real time. It is tricky because there's a lot of stochasticity involved with both decision levels. So one approach I would recommend is like you devise a plan of the report times for the extra board roster, and then you use this framework to kind of simulate the performance of that plan and from there you can revise, go back and revise your original report times if possible. Yeah, so that's one way how I envision things can go.
Thank you very much. Okay, we're going to go back online. The next speaker is Mohammed Ansari Ismail. He's a NENSERC postdoc fellow in the Department of Civil and Mineral Engineering at UT. He earned his master's in energy and environmental systems and his PhD in transportation engineering from the University of Calgary. He has worked on several industry and consulting projects for partners such as Calgary Transit, IBI Group, and Future. His research covers diverse topics in transportation engineering, including nervous system resilience and vulnerability, public transit modeling, intelligent ITS, behavioral modeling, and big data analysis. And his presentation is Metro Transit System Vulnerability, Understanding Factors Affecting the Severity of Disruptive Events. So,
yeah, thank you so much for the introduction. Can everybody see my screen?
Yes, we can.
Awesome. I actually modified the title to match, better to the content of today's presentation. So today I'm going to talk about subway transit system vulnerability using the Toronto subway network as a case study. So urban rail transit systems, including the Toronto subway network, are essential for everyday travel, but they're also prone to unplanned disruptive events, from technical incidents to operational incidents and passenger-related incidents. While the probability of these events is quite low, their impact on the network is substantial when they occur in the system. So today I'm going to basically present a data-driven framework that combines historical incident data and also passenger demand data to identify where in the system, what parts of the system are most vulnerable and why. We all know that access to reliable and resilient public transit system is crucial to all users. So for many people in Toronto, the Toronto subway network is a primary way of getting to work, to school, and also other essential services. However, the Toronto subway network, similar to other transportation network, experience frequent unplanned disruption. And the severity of these disruptions ranges from a few minutes to incidents that can last for several hours in the system. The point is that these pressures are not evenly distributed in the Toronto subway network. So Toronto's Line 1 and also the major transfer hubs carry the highest volume of passengers, and they have the most complex operations. So they usually experience the heaviest pressure and increasing travel time when those disruptions occur in the system. So there is a need for a data-driven method to identify where the network is most vulnerable. So which stations, for instance, in the Toronto subway network are most vulnerable. So when we talk about vulnerability, there are basically two sides to the problem. So the first side is the consequence of the incident. So basically, when something goes wrong, how does that really hurt the system? And we usually measure the consequence in terms of the increase in travel costs of the network, and also lost ridership due to origin destination disconnection in the system, because some of the stations are going to be out when we have some incidents going on in the network. The second component, the second side, is the incident probability. So some stations in a rail network are more prone to disruption. So these could be stations, with higher ridership, with aging infrastructure, or also with more complex operation. And because of this, they experience higher incident frequency compared to the other stations. So basically, there are, as I mentioned, two sides to the vulnerability problem. So vulnerability is not just about where the incidents are most damaging to the network, but also where those incidents happen more often. So this leads us to the objective of this study, which is, so the first objective is to propose a vulnerability index that captures both the probability of a station failure and consequences of disruptive events. And based on this measure, we are going to rank stations from the most to the least vulnerable. And finally, the third objective is to develop policy recommendations to improve network resilience, for instance, by strengthening the infrastructure or allocating more operational resources. In terms of the scope of this study is basically focused on incident taking place in Toronto subway network, but the methodology is general enough to be applied to like other rail services, urban rail services. For this study, we are relying on two main data sources. So the first one is historical incident database from 2018 to 2023. There are more than 45,000 usable incident records. And for each incident record, we have date and time, the type of incident, station, line, and the duration of the delay. The second database is the OD demand matrix, which is derived from the 2016 Transportation Tomorrow survey, and it includes hourly OD flows between all station pairs. And we use this data to basically estimate network-wide lost ridership due to the disconnection of OD pairs in a network during disruption. So before talking about the vulnerability of the stations, let's talk about why we need to model the probability of station failure. Station level incident occurrences vary systematically due to several reasons, including ridership volume. So we're expecting that, for instance, the stations that carry higher volume of passengers are more prone to passenger-related incidents. Also, stations with operational complexity or those that function as transfer hubs, they are exposed to frequent movements of trains, so they are possibly more prone to operational and technical incidents. And also, stations with aged infrastructure, they are also more prone to technical incidents. So to capture all this, we need a statistical model which considers the station failure probability defined as the likelihood of at least one incident in a given day at a given station. So this is basically an efficiency-based kind of risk-based approach, and the probability is basically this is an important input to the risk-based approach, because we need to consider for risk-based approaches both the probability and consequences. So we obtain the probability of a station failure using the negative binomial regression model, in which the outcome is the station failure probability and the predictors are the station usage. That's basically the boarding and alighting activities at different stations in a network. We're also looking at historical incident frequency as a predictor. We also have transfer station indicator and peak and off-peak period indicator. So whether the station is labeled as a transfer station or not, or let's say the station is operating during peak period versus off-peak period. And here I have summarized the findings. So we find that the station usage has a positive significant impact on the probability of a station failure. So basically, stations with higher ridership are more likely to experience incidents in the future. Also, similar to that, historical incident frequency was statistically significant, and that's a strong predictor, which means that the stations that have had experienced incidents in the past are more likely to experience incidents in the future as well. In contrast to the first two, transfer station indicator and peak and off-peak indicator, so they are not statistically significant. So that just means that being just labeled as a transfer station or operating during, let's say, peak period doesn't add much explanatory power for obtaining the probability of occurrence. This map right here actually shows the spatial pattern of the probability of a station failure. I have just labeled the top 10 stations in a network. And basically the larger red circles shows the most vulnerable, the stations with the highest probability of a station failure in the network. So these top stations, 10 top stations, represent 13% of the network in terms of size, but they account for 30% of the daily ridership in the network. And 5 of these stations are the busiest stations in the network, including Blue Ridge on line 1 and line 2, St. George on line 1, Union, and also Eglinton station. as I said before, since these stations, I mean, the one important factor is being exposed to passengers. So since these are like the busiest stations and they are exposed to passenger activities, so they are more susceptible to passenger-related incidents. So that could possibly explain why these stations, experience more frequent incidents. Also, 7 of the top 10 stations are on line 1. Which is basically the oldest and the busiest line in Toronto subway network. And that basically highlights the combined role of high ridership and aging infrastructure, which makes these stations actually more prone to both technical incidents and also passenger-related incidents. Okay, so why do we need to basically propose a new vulnerability index instead of just relying on the existing measures? Traditional measures mainly focus on the network structure and the shortest path between the OD pairs in the network, but they usually ignore the probability of a station failure. They also ignore historical incident records. So what they usually do is to just assume that, for instance, they are just running a simulation, just removing stations in the network one by one, and then measuring the impact to identify the most vulnerable stations. And finally, they don't account for the lost ridership from the disconnection of OD pairs in a network. Our index aims to capture like 3 things at the same time. So the probability of station failure, the network-wide efficiency loss from historical incidents. So we are just looking at all of those 45,000 incident records that I mentioned before, and also demand-weighted ridership impact. So OD pairs that carry more passengers, they count more in our approach. I'm not gonna go deep into the methodology. I'm just gonna provide a quick overview of what we have done. So this is like the vulnerability analysis, and the core of our vulnerability index is a global efficiency. And that's basically a concept borrowed from, graph theory and network theory. So under normal operation, when nothing is wrong, this is like the state 1 of the network, the efficiency of the network is calculated using this equation, which basically sums the inverse of the travel distance, shortest travel distance between every OD pair in a network, weighted by the ridership between OD pairs. During disruption, the approach is similar. So again, it sums basically the inverse of the new travel distance, the updated travel distance, because when we have some incident in the network, we have some rerouting and increase in travel costs, so we have to update that, again weighted by the ridership between the origin and destinations across the network. And we also have like this connectivity indicator, which is 1 when the OD pairs are still connected, and is 0 when we have like this connectivity between the OD pairs. We combine those with the station failure probability that we discussed to make it a risk-based approach. So we have like the consequences right here, and we have the probability right there. And finally, we calculate the performance loss in terms of how much each incident degrade the performance of the network. So since we have more than 45,000 incident records, we are repeating this analysis for all of those incident records. So we have like a pair of a station, incident record for which we are doing this analysis. So here I want to explain how we move from a single station incident pair or single loss value for that to a vulnerability profile for every station in Toronto subway network. So as I mentioned before, we obtained a single loss value for every station incident pair in the system, right? And since there are like 45,000 of them, and since stations in Toronto subway network experience many incidents over the study period, we get a distribution of the loss values for every station in the Toronto subway network. And the results are represented over here as these violin plots. So in here, we have like individual plots for every station in the network. And in these plots, higher violins means basically that the performance losses, where most of the performance losses lie. So the higher violins means that the incidents on that specific station basically causes more performance loss to the network. The width of the violin, on the other hand, is basically showing the variability. So the wider violins basically indicate that the incidence or the impact of incidence on that specific station is more volatile. So characterizing each of these distribution by its mean and standard deviation, we create a composite score to rank the stations and compare the stations in terms of vulnerability. And this is basically the heat map of most vulnerable stations in the Toronto subway network. Again, I'm just labeling the top 10 stations. And I mean, the larger red circles shows, the most vulnerable ones, right? So for instance, North York Center over here. So two clusters stands out here. So the first one is the transfer stations in downtown area, including the Blue Ridge on line 1 and line 2, Spadina on line 2, and also St. George. Even St. George is one of them. It's not top 10, but it's one of those with relatively high vulnerability. And these stations usually experience high interconnectivity because, two transit lines meet at these stations, and disruption can easily propagate across the network when they are out. They also have very high operational complexity because of very high frequency services and also, frequent train movements. And they also experience high ridership, which basically pushes the vulnerability score of these stations to the top because of the vulnerability and exposure to passenger-related incidents. The other branch, or cluster, is basically the northern branch of line 1, roughly from Blue Ridge to the North York Center. So this part of the system is basically the oldest and the busiest section of line 1, basically. And it makes these sections actually prone to both passenger-related incidents and technical incidents. So while ATC signaling systems and the newer rocket trains kind of modernize the train control and rolling stock on this northern branch of line 1, the other supporting infrastructures are still kind of old. So that makes this part kind of prone to both still technical and passenger-related incidents. These vulnerability discussions can be translated into policy implications for TTC. So from operational perspective, incidents that show high vulnerability should be prioritized, need to be prioritized with incident mitigation and also probably faster response capacity, especially for those along line 1. Also, since passenger-related incidents account for a large fraction of delays, there is a need for measures that reduces their frequency and improve their response time, whether it's through, let's say, staffing, platform management, or faster emergency responses. From an infrastructure perspective, much of the vulnerability for those along line 1 is basically tied to the aging infrastructure. So upgrading the infrastructure along these lines can reduce both technical and operational disruptions. The results highlight the importance of improving the redundancy around the northern branch of line 1. So that part of the network lacks basically alternative routing options when disruptions occur on that part of the network. So improving parallel routing options can reduce the network-wide impact when we have some incident going on that part of the network. So that concludes my presentation today. So just in summarizing the key inputs, key outputs of this presentation. So incidents, as we discussed in the Toronto subway network, are not evenly distributed across different stations. We discussed that the station's vulnerability depends on both probability and also the impact. Our approach basically provides operation or captures operational reality better than structural baseline models because we take into account historical incident records, the probability of a station failure, and also the lost ridership due to OD demand or OD pair disconnection in network. We also discussed that stations with highest vulnerabilities are along line 1 and also those key transfer hubs. And we also discussed the policy implications and the fact that the outcomes of this study can guide research allocation, infrastructure upgrades, and incident management in the system. Thank you very much for listening. I'd be happy to take any questions or comments.
Any questions from the audience or from online?
No online questions.
Okay. Well, you do have one. Good.
Thanks for that. I think you mentioned that you studied a 4 or 5 year incident period. In that period, did you see any trends in terms of number of incidents? Are they rising, declining? Are the hotspots changing over that time?
Oh, that's a great question. We haven't actually, but yeah, but that's a good idea. So I mean, specifically since the ATC signaling system is introduced in September 2022. I mean, we could do some analysis to especially compare the performance of line 1 and especially the northern branch of line 1 before 2022 and after 2022 to see how like the modernized equipments actually help the system to become more resilient. We haven't looked at it, but yeah, we are going to do that for sure.
Mohammed, I have a question. The TTC's network is very limited. And I was just curious, it's not what you were researching, but just based on the research you did, for networks that are far more complex with more transfer points, I know there's been a fair amount of research that's looked at resilience, and you mentioned vulnerabilities. What's your feeling about how your analysis would deal with, networks that were more complex, so the better resilience, but also more transfer points, which are a point of vulnerability?
Oh yeah, that's a great question. I mean, as I also mentioned during my presentation, the methodology is kind of general, so it can be applied to any rail network. I would say the only challenge would be the availability of the data. I mean, for the Toronto subway network, we were fortunate to also have like the OD demand data and also historical incident data. But I mean, that could be a challenge for other networks. Depending on the policies and when it comes to data sharing and so forth. So I would say that would be the only challenge. But as soon as we have like all the necessary information, we can do this analysis for every transportation network, because the core of the vulnerability index is still topological. So that's what we are currently working to improve based on the Wi-Fi data in our second project. But for this specific one, since the core is topological, it just graph theory, so it can be applied to any network.
Yeah, another question. This is probably way beyond sort of the strategies you mentioned about platform management and so forth, but it would be interesting to look at the location of crossover tracks, of where trains can be, short-turned and rerouted, and whether the choices that were made are valid in terms of the vulnerability index, and also whether there are locations where there should be new crossover tracks.
Yeah, that's an awesome point. So one thing, I would say that's one limitation of our study is that we are just solely looking at the Toronto subway network and not the interaction of Toronto subway network to other like networks, streetcar network, bus network. So for instance, when we have some disruption going on, there are like many passengers using other alternative services, transit services to just, for the rest of their trip. So what we are going to do in our second project is to just rely on the Wi-Fi data. So we do have like the Wi-Fi data from which we have derived the trajectory of the passenger throughout the network back in 2021 and 2022. And since we have like the incident data, we are matching them to drive basically the real choice of passengers. And that way we can somehow maybe also catch the interactions between the Toronto subway network and like other networks, alternative basically modes provided to transit users.
And that's a good point, but I was just thinking of the crossover tracks for the subway alone.
Oh, crossover. Oh, for the subway alone. Okay.
In terms of being able to respond to the length of the delay and so forth. There are very limited number of spots where the trains can be turned around.
We haven't looked at it. Yeah, that's also, depending on data availability, we can also look at that one too.
That sort of thing. Yeah.
Okay, we have one online question. So one of the audience is saying, do you expect that line 5 opening to cause more incidents at their 2 transfer connections with line 1?
Sorry, just let me read it again. So line 5 opening to cause more incidents at their 2 transfer connections with line 1. That's a tough thing to answer because it all depends on. We have to like collect data to see the impact of introducing line 5 and interactions between the 2 transfer stations with line 1 and line 5. Not quite sure, but one thing that I'm sure about, so when you're introducing a new service, so you are generating demand for it. And because of that, sometimes, for instance, for like the last station in line 1, which is going to be the transfer station to line 5, there will be more demand for that specific line station on line 1 in future. And that makes that station more prone to passenger-related incidents. So, what I can think of is that since it generates more demand for that specific station, so it's going to be more prone to passenger-related incidents. And based on another study that we have already done, so passenger-related incidents are basically the ones that the network is most vulnerable to. So they are like, in terms of duration, in terms of severity, they are the worst one compared to operational and technical incidents. So possibly yes, but we need to like collect more data to be sure to answer that question.
Okay, thank you very much. So
thank you.
Our last presentation is back in the room here with Jillian again, but on a totally different topic, modeling the Toronto path with GTFS pathways.
All right. Hello again, everyone. Welcome to my second presentation. This time I'm modeling the Toronto path with GTFS pathways. So a quick outline of this presentation. I'll first introduce you to the Toronto path for those of you who are not familiar with it. And then I'll go through the research motivation, the objectives, methodology, and results. So the Toronto path is an indoor pedestrian walkway network that's in downtown Toronto. It is mostly underground. It is very extensive at about 30 plus kilometers long, and it connects over many important office buildings in downtown Toronto. So this is heavily used by commuters who work in the downtown area, by the residents in the area, and because of its indoor nature, it is heavily used in the winter. So the Toronto Path Network provides easy access to the transit network. For example, it connects with the Toronto Subway Line 1 at 6 stations. It also connects with 6 streetcar routes operated by the TTC. The path connects with Toronto Union Station, where you can get on trains operated by GO Transit. So those are regional trains, and also operated by VIA, national and international trains. And also you can walk to the Union Station bus terminal, where you can hop on regional and long distance buses. So as you can see, the path makes up a very significant portion of downtown Toronto's transportation network. But despite its major role, there's currently no digital and parsable model of the path. Therefore, it is often overlooked in accessibility and travel analyses for downtown Toronto. And some maps of the path currently exist. For example, City of Toronto has a official map, but that is in the PDF format, so it is static. And there are some proprietary software that maps out like shops and restaurants at various sections of the path, but that is not in the desired format for analytical studies. So because of this, we would like to develop a digital model of the path that's in a desirable parsable format and preferably interoperable with transit data. So because of these requirements, we've identified that the GTFS pathways is a very good data standard for this task. So why do we choose the GTFS pathways? So to start with, the GTFS, which stands for General Transit Feed Specification, is a very popular data standard to convey transit information. It is used by over 10,000 transit agencies all over the world. And GTFS pathways is a relatively new extension to the GTFS that details the layout of transit stations. So in GTFS pathways, the layout of stations is essentially described by a network made up of nodes and edges. And also it describes the geometrical attributes of various circulation elements like walkways, stairs, escalators, etc. It is great for indoor navigation. And to the right, you see an example implementation of this data standard on a Vancouver SkyTrain station. So even though the path is not a subway station or train station itself, we still want to use the GTFS because it is a robust format. And also it provides good access to the transit system. So when converting the path into GTFS pathways, we're going to call major buildings or major underground areas as quote unquote stations in the GTFS terminology. And next we move on to the methodology. So we conducted some preliminary research. So first we studied the data structure of GTFS pathways, and we've identified that there's quite a bit of data requirement necessary to build this model. So for example, we need the accurate locations of building entrances and the start and end of walkways and locations of stairs, etc. And we've also looked into effective field data collection tools to meet these requirements, as well as a method to store the field data so that it can be translated into GTFS pathways later. So now we move on to data collection. So this is actually quite a big challenge within this project because different sections of the path is managed by the property owners of the building under which the path runs through. So as a result, the design drawings are often not available due to privacy reasons. And accurate latitude and longitude coordinate readings can be very hard to obtain because the path is mostly underground. So because of that, we've experimented with various field data collection methods. So we have some manual measurement methods. And when we do have design drawings available in the CAD format, whether that's provided by the property manager or that may be obtained from the city's planning application portal, we've designed a tool to automatically get the coordinates of important points from these drawings. So I'll give a quick overview of some of the methods we've explored. So first of all, there's LiDAR. So LiDAR scanning is actually available on many iPhone Pro models. So what it does is that you can take a quick scan of a room or like a kitchen or something, and that automatically generates a floor plan for you. But this was not a great fit for the path because the path has a lot of large open spaces, and the reflective walls and panels can really throw off the scans. So we decided ultimately not to use this. And we've also explored the possibility of using Bluetooth beacons. So the idea is that you place a system of beacons, like at least 3, at locations where you know the exact coordinates. And then you use the signal strength reading from these beacons to estimate the distance from these beacons. So from that, you can triangulate your location. So you can see here that you can get these readings from a smartphone app, but we tested a system made up of 4 beacons, but ultimately this didn't work out as we expected because sometimes beacons give different readings when they're at the same distance, probably due to interference. And then the readings often fluctuate quite a bit, so that induces some errors as well. And we tried some conventional devices. So for example, handheld GPS, like we can get that from our phone, but this doesn't quite work very well because of the urban canyon effect in downtown Toronto. And also there's a handheld compass, which can help us to determine the orientation of walkways. But we found that this had pretty low accuracy when underground. But luckily, a lot of the walkways are there so that they line up exactly parallel or perpendicular to the street grid. So we can use that as an estimate for the orientation. So the one device that worked quite well for us was a measuring wheel. So we can use that to reliably get the widths and lengths of the elements we want. So because of the limited options we had, at many places we had to resort to approximation methods. So this is especially useful when we had to do quick walkthroughs at very large underground spaces. So the most common method is like whenever I'm standing at a location underground, I try to see how that aligns with important landmarks on the street level. So whether that's building entrances or the street grid. And that was all the manual collection methods. And when we do have CAD drawings available, we designed a CAD-based tool to automatically get the coordinates from of important locations from a drawing. And then from there, we can calculate the exact coordinates as long as we know the coordinate of just one point on that drawing. Okay, so moving on to the next phase. So after collecting the field data, we've identified the OpenStreetMap, or OSM in short, as a good intermediate database before we convert that into the GTFS pathways format. So why do we choose OSM? One big reason is that OpenStreetMap is an open and collaborative database, so anyone can use this data for future research. The OSM's data is in a intuitive structure, so you can see on the right that it's in the tag value kind of data, so that can be easily translated into GTFS later. And also, there has been some attempts to map out the path at various sections in the past. But we do see that a lot of that existing data lacked good accuracy and was missing data that was required to GTFS pathways. So we have to be very careful in updating that data and also to reflect recent changes to the path network. So for the OSM update task, we use this open software known as JOSM. So we've essentially added all the nodes and edges that make up the path to what's known as a relation, which is a collection of all the elements that define the path. So you can see a section of the path in the editor to the right. And now we go to the final phase, which is converting the OSM data into GTFS pathways. So for this task, we've developed a Python-based converter. So the idea is that you take the OSM data and convert it to a network X graph. Network X is a Python package. That gives you the network representation of the path in a like nodes and edges format. And from there, we translate the OSM data structure to the format that's detailed in the GTFS documentation. And the output is mainly the two files. We have stops.txt and pathways.txt. So we'll look at each of these right now. So nodes in GTFS pathways are stored as entries in stops.txt. So example node is an entrance of a building, which is part of the path network. So calling these nodes as stops sounds a bit weird or counterintuitive, but since GTFS was originally a transit-specific data standard, that is the terminology they use. So at the bottom, you see the entry that corresponds to this entrance. And then edges are entries in the pathways.txt. So in each entry, we have the from stop ID and to stop ID. So these refers to the nodes that was detailed in the stops file. And each edge has like one of these modes. So the modes we have here are walkways, stairs, escalators, and elevator. And also there are some like geometric attributes associated with these pathways. So after the conversion to GTFS pathways, another thing we did was we developed a tool to automatically generate CAD-based floor plans from the GTFS dimensions as an input. So this can be used for pedestrian flow analysis. So we see an example here. So this is an example section of the path. So on the left, we have the raw OSM data, and to the right, we have the floor plan. So we'll see this a bit later again. And now let's talk about the results of the data that we can do for now. And also, I will also discuss some future prospects of what you can do with this data in the future. So one very obvious application is trip planning and travel time analysis. So currently, Google Maps, like that's a very popular navigation app, does not recognize the path as a viable option for pedestrians. So for example, if you want to walk from the Toronto Eaton Center to Union Station, even though they are interconnected with the path, Google still wants you to walk primarily on Yonge Street. And the approximate distance is about 1.2 kilometers. And the walking time, 17 minutes, that's calculated based on the distance divided by the average human walk speed. So that does not account for the wait time behind traffic signals. So on the other hand, if we do the same trip in the path, this is the path that you want to take. So obviously, this provides a safe and climate-controlled environment, which is very desirable in the winter in Toronto. And another benefit is that you will no longer be stopped by traffic signals. So even though this route is somewhat longer than the street route, the fact that you don't have these traffic signals means that this is probably going to be faster as well. And another thing we did was we ran this test simulation for pedestrian flow analysis. So to the right is an example scenario in case of emergency. So from this, you can look at the level of service at various sections in the path and identify important bottlenecks of the system. And during the updates to the OSM, a lot of the accessibility infrastructure has been mapped out. So for example, we see like these lifts, wheelchair lifts to bypass stairs. So this information allows us to study the ease of access for users of path who may have a disability. And now we talk about sort of the future prospects. So we can integrate this pathways model with the broader GTFS schedule. And ideally, we want to integrate it with multiple agencies that operate some kind of transportation mode in the downtown area. So with that, we can study the path's role in potentially first or last mile option to transit connection, and how it can act as a good transfer among different nodes. And finally, this lays the foundation for development of the digital twin for the path. So a good use case is variable wayfinding signs to guide pedestrians in case of congestion or emergency. So what I can think of is like, you can sort of guide pedestrians when there's a big event like Taylor Swift concert or the upcoming FIFA World Cup. And yeah, I would like to acknowledge the project funders, WSP Canada and MyTax. And special thanks to property managers of these buildings for their permission of site visit. And I would also like to shout out the Toronto Association of BIAs and the Financial District BIA for their support of this project. And yeah, thank you.
That was a fun one to end up on. Any questions here or the online? Well, I'm afraid I do. So what percentage of the entire path you got cooperation from in terms of CAD drawings, just roughly? A quarter, half, 3/4?
Like 10%.
10%.
Yeah.
Okay.
How many meetings did you have?
Well,
that percent.
like 2 maybe?
Two,
Not
two
that
per,
many.
two per property.
No, just one, like 2 in total.
2 in total?
Yeah.
So you just,
Yeah, there was a meeting that involved the BIA and a lot of
okay, and they brought them all together.
Yeah,
Okay,
yeah,
okay.
exactly.
And then you got the CAD drawings and stuff. How did you go from the OSM raw data to the floor plans? I mean, did you go out with a measuring tape for all those little passageways?
No, it's mostly the passageways that like you would normally use You're in the path system.
But you had all the exits and stuff.
Uh,
I mean,
well,
there's lots, it's a rabbit's warren. I mean, there's lots of little
Yeah.
passageways everywhere.
yeah, there are many little passageways,
But that's what you were doing, was just measuring with like a laser or something?
yeah, with the measuring wheel. But I mean, I didn't like map out every single like little passage.
Well, it looked like you had quite a bit of detail, and then I guess the question is, how many times did you get stopped by security asking what you were doing?
Like we did ask for permission to do those site visits from many property managers. Like
Okay.
even though they didn't provide us the drawing directly.
Okay, they
like,
let you
yeah,
use
that
the
we-
wheel. And
Yeah,
stuff.
exactly.
Okay.
So that was good. Yeah.
Well, congratulations. That's
We have one online question for Jillian. Somebody's asking, how did you deal with stairs, or how to deal with stairs?
Stairs, in terms of like measuring the length, there's quite a bit of approximation involved. Like I try to look at the number of steps for each stair and just try to multiply that by the estimated like width of each stair. So that's one thing I did. But in many places, it was an estimation, because at the end of the day, it is a network model that I just want to make sure that the stairs are there, right? So the exact location is not the top priority. So yeah.
But the beginning and the end of staircase, those were properly quoted.
Yeah, exactly.
Okay, well, thank you again.
Okay, well, thank you so much for those who stayed to the very end. Really appreciate your participation, and for those online as well. So this brings us to the end of this event. I hope you had an idea of some of the ongoing work and some of the recent work that was accomplished here over the past 2 days. And we look forward again to having you next year. But again, one more time as a reminder about the Transit Data Symposium that we're going to host next year in June of 2026. Again, if you have any papers, any interesting work that you'd like to share with the wider global community who's interested in data-driven transit solutions, the deadline for the submission for abstracts is December 12th. So please feel free to submit your abstract. Okay, with this, I bring this to a close. Thank you very much, and see you next year. Bye.